Okay, from the last video, we had this statement here, which is read as follows. The curl of a gradient is 0. So curl of a vector field is given by del cross, and of course, del G is our symbol for the gradient of G. This can also be phrased like this. Right? Because if f is conservative, then it is the gradient of some potential function. So the curl of that conservative vector field would be 0 because it is the gradient of some function. The opposite statement is true sometimes. So that is to say, if you know that the curl of a vector field is 0, sometimes you can conclude that it's conservative. This is theorem 4 on page 1145, and I'm just going to state it in a little bit broader context. Okay, so if your vector field happens to be defined on, for example, all of R3 or something, but more generally on any simply connected region, so simply connected means that it doesn't have any holes in it, assuming that its component functions have continuous partial derivatives, then the curl of the vector field being 0 means that it's conservative. So it means that it's a gradient vector function, it means it's path independent, and so on. Okay, so that's a nice little theorem before we move on to some examples. I'm going to use sort of everything that we've learned about curl and divergence and gradients and so on to answer these questions here. So is there a vector field G that has its curl equal to this right here? Now, one option to investigate this question is to write out in general what the curl of a vector field is in terms of the partial derivatives of its component functions. But another option is to use something that I had up here. So, for example, if this vector field here is to be the curl of some vector field, so the curl of the vector field G, then if I take the divergence of that, it should give me 0, right? So again, del cross G in this case would be the curl of G, and divergence of curl is supposed to be 0. So if this right here is indeed a del cross G, then if I take its divergence, I should get 0. So one way to check to see if there's a vector field that can satisfy this is if I could just take the divergence of this expression. So let me compute this right here. Okay, remember what this is. The nabla operator is a vector that has each of the partial derivatives in it. So when I dot it with this expression, I'm taking the derivative with respect to x here, y here, and z here. Let's see what I get. Oh, this is 1, right? Which is not equal to 0. So I've just concluded that G, there is no such G. Again, going through the logic again, if there was a vector field G that had this curl, then the divergence of that curl would have to be 0. But since the divergence of that vector field is not 0, this thing could not possibly be curl. So that's kind of slick, right? Okay, in this one, actually in the next two examples, we're going to be verifying some identities. So this is just a practice working with the divergence and curl operations. So in this example, I'm starting with sort of an arbitrary pair of vector fields. Let's say F is like P, Q, R, and then G is M, N, L or something. And I want to prove that if I take the cross product of the vector fields and compute the divergence, then there's sort of this product rule thing happening here. Well, I mean, I don't know if you can call it a product rule because it doesn't really look like a product rule, but you end up getting the dot product of the G vector field with the curl field of F minus the F vector field dotted with the curl vector field of G. So it's sort of an interesting, I guess you could call it a product rule type thing here. So let's see that it's true. Let's compute on one hand the divergence of f cross g, and then on the other hand these expressions, and see that they're equal. To compute the divergence of this expression, I take the partial of this with respect to x, with respect to y, and so on. Now look, Q and L, for example, are three variable functions, right? They are multivariate functions that serve as the component functions of these vector fields. So when I take a derivative, I need a product rule here. Okay, let me see where I'm headed here. I'd like to end up at g.curlf minus f.curlg. So let me kind of expand that and see what it looks like, and maybe I'll fill in the details. Hopefully the algebra will transform this line into this line. So did not leave myself room here, but you can see up here we started with the divergence of f cross g on the right-hand side, on the left-hand side, and I expanded that out to this. And then on the right-hand side, I have g curl f minus f curl g, and that is written out in component form like this. Let me perform the dot product and cross my fingers that I get what I have written up here. Okay, let's try and find, you know, each term on this line in this line. Let's see if they're there. Okay, indeed, every term is accounted for in between these two lines. So I have myself a proof. The divergence of f cross g is indeed g curl f minus f curl g. So that was fun, right? Let's verify some more identities. These shouldn't be as painful. So in this example, we're given a vector field. This is a 3D vector field R, component functions x, y, and z, and R is standing for the magnitude of that vector field. So R in this case is square root x squared plus y squared plus z squared. Okay, and I'm going to verify one by one these identities here. So the gradient of this multivariate function R is supposedly equal to the vector field divided by R. Well, indeed, we have the gradient of this R function is our vector field divided by its magnitude. Now we're going to compute the curl of this vector field. Each of these partial derivatives I'm taking are sort of mixed variables. So for example, the partial derivative of z with respect to y is 0. Yep, indeed, I'm getting that the curl of this vector field is 0. I like to put vector hats on all my vector functions. Okay, on to identity C. We're going to compute the gradient of 1 over the R function, the magnitude of the vector field, and see that it's equal to this. Yep, it looks like I have the vector field R divided by the magnitude cubed. Okay, and lastly, I'm going to take the gradient of the logarithm of the r function and verify that it's the vector field over r squared. Yep, and we have it. On top we've got xyz, and the 2's cancel, and we're dividing by the square root of this expression squared. Okay, the last thing that I wanted just to remind you of is that curl and divergence appear in the two statements of Green's theorem. So we had looked at these theorems in isolation in a previous section, but now we understand why the double integrals are actually computing, some quantity relative to the vector field. So when you take this double integral in the first half of Green's theorem, you're sort of summing up all the rotation of the vector field across the region. And that ends up coinciding, Green's theorem says, with the circulation of the field along the boundary. And in the divergence form, you're sort of summing up the tendency of your field to diverge from points all across the region. And that ends up coinciding with the flux of the vector field across the boundary. We'll talk about flux more when we get into the other theorems of this chapter. But anyway, now we know what curl and divergence is.